Okay, so we're going to continue with the last properties on the transform, which is a convolution. Okay, so if we have two signals here, we have xt and yt, so both are having a transform of x omega and y omega respectively. If xt is said to be convolved with yt, so this is a symbol of convolution. Okay, so the results in terms of its frequency domain will be simply a multiplication of x omega and y omega. Okay, whereas if we are having a multiplication in time domain, xt multiplies yt, so in frequency domain, it should be 1 over 2 pi convolution of x omega and y omega. Okay, so this is the properties of convolution for transform. So let's have a look at these examples. So we are given systems where a linear time invariant system, we have the input of xt given to be 5 over pi sinc of 5t. Then there is a feedback signal of h1t, and we are given h1t is in terms of this Fourier transform where we have h1 omega of 2 pi delta function omega minus 100. So multiplication between xt and h1t will give us the yt, the output of the system. Okay, so based on the questions, number one is to find the Fourier transform of the input signal of xt. Okay, let's have a look on how to find this the Fourier transform. Okay, so this is what we have been given in the question just now. We are having xt, which is 5 over pi sinc of 5t. We are given h1 omega of 2 pi delta function omega minus 100. Okay, so from the table, if you want to find the Fourier transform for xt function of sinc here, we can note that there is no such a sinc function in time domain based on the table here, right? But there is a sinc function in frequency domain which is for rectangular. So by right, to find the Fourier transform for sinc function, we need to adopt the duality properties that we have learned previously. So in duality properties, this is based on the table here. So if you are having the A of rectangular t over tau, so its Fourier transform should be a tau sinc function of omega tau over 2. So by using duality, we can write that these terms now become a tau sinc of t tau over 2, and its Fourier transform will be 2 pi of a rectangular omega over tau. So we just simply change the t to omega. Okay, so this is the duality properties. Yeah? So in order for us to find a Fourier transform for 5 over pi sinc of 5t, so we need to use this transformation down here. Okay, and we need to compare the terms that we're having here and the terms that we are having here. So when we compare those terms, we are to see that a tau shall be equals to 5 over pi, and tau over 2 will give us step 5. So based on that, we shall have tau equals to 10, and as such, your A will be 5 over pi multiplied with 1 over 10. So that will give us A should be equals to 1 over 2 pi. So we're going to substitute this A and tau in here. So we're going to get the 5 over pi sinc of 5t will give us 2 pi A rectangular omega over tau. So that will give us rectangular omega over 10. So that's the answer for a Fourier transform of 5 over pi sinc of 5t. Okay, so let's have a look on the second problems here. So we need to find the Fourier transform for yt. Yeah, Fourier transform for the yt. So we need to operate the multiplication between the input and the feedback signal. Okay, so basically based on the diagram, yt shall be equals to xt multiplied with h1t. So in Fourier transform, by using a convolution properties, we shall have y omega equals to 1 over 2 pi x omega convolved with h1 omega. Yeah, because in time domain is xt multiplied with h1t. So in frequency domain, it should be x omega convolved with h1 omega. So as such, we're going to get the value to be 1 over 2 pi rectangular omega over 10 convolved with 2 pi delta function omega minus 100. Okay, so 2 pi and this 1 over 2 pi can be cancelled out. So when we consider a convolution between rectangular omega over 10 and delta function omega minus 100, it seems that convolution means that the rectangular function here shall be shifted, shall be moved forward or shall be shifted to the position of this impulse function. So we need to shift omega to this position, a shifting by 100 positions to the right. So as such, you're going to get the rectangular function should now be omega minus 100 divided by 10. So that should be the answer for a Fourier transform of the output item. Okay. Right. So we shall proceed now. Hopefully you understand about the convolution properties. Now we're going to have examples on past year's questions and the test questions. For these examples, we need to find the Fourier transform for the following signals, the GT and HT. So let's have a look on the solution. Okay, so we are given the GT as 3 rectangular 0.25t plus exponential negative 2 modulus of t. So this is nothing much. You just have to compare. You just have to refer to the table. To the table. You have to get the GT in Fourier transform with G omega. So this need to refer to the table. Okay, so you're going to get 3 times 4 sinc function omega 4 divided by 2 plus. Okay, so when you refer to the table, you're going to get this. Yeah. So if I can pinpoint the position, I mean the signals that we are dealing with. Okay, so rectangle should be here. You need to use this transformation, and the other one you need to refer to this. Yeah, this is the one. Yeah. Okay, so you're going to have the G omega, the transformation of the GT. This and that. Okay, the next one is a 9 sinc squared of 40. Okay, so in time domain, you can refer to the table. There is no such sinc squared function on the left. Okay, there is no sinc squared function on the left. So in that case, you need to use a duality properties to solve for it. So in duality properties, you need to adopt the triangular function, because in triangular we have in frequency domain we have a sinc squared. Yeah. So by using the duality properties, we can say that when we have a triangularity of tau, okay, we're going to have a tau sinc squared omega tau divided by 2. So by using the dualities, we're going to have a tau sinc squared t tau over 2, and its respective transform will be 2 pi of a triangular omega divided by tau. Okay. Next task is that we need to compare the given problems and this value or this term such that we can obtain the a and tau. Yeah, the a and tau. So when we compare the value, then we're going to see that tau over 2 will be equals to 4. So which will lead us to tau equals to 8. And a tau will be equals to 9. So we're going to have a as 9 over 8. So we substitute a and tau into this. We'll have these terms here. Yeah, 9 sinc squared of 40 will be 9 pi over 4 triangular of omega divided by 8. Okay, hopefully it's clear. Yeah. Okay, okay, and for these examples down here, I need to obtain the Fourier transform for this xt, which is exponential negative modulus t cos of 10t. Okay, so let's have a look on the solution for this problem. So we are given this xt of exponential negative t modulus cos of 10t. So from the table, you can refer to the table, you're going to get exponential negative modulus t will give us 2 over 1 plus omega squared. Okay. And since in this problem, we have multiplication of exponential negative t modulus with cosine of 10t. So by right, since we have a cosine function, we can adopt a modulation properties. So in modulation properties, we are given this, yeah, xt cos omega naught t. So this will lead us to a Fourier transform of half x omega minus omega naught plus x omega plus omega naught, such that when we have exponential negative t modulus cos of tan t. This will give us what? Half. So that will be x omega, right? So x omega, so we're going to have x omega minus omega naught plus x omega plus omega naught. So that will be the answer for this problem. Okay, and last questions here, we need to find the inverse Fourier transform of y omega equals to 8 pi delta function omega minus 5 plus 8 pi delta function omega plus 5. So find the solution for this. We can straight away refer to the table. So the table states that when we are having signals of exponential j omega naught t, so its respective transform will be 2 pi delta omega minus omega naught. So straight away, we can see that when we have these terms here, we can write that the inverse Fourier transform will be, that terms will be 4 exponential j of 5t, and for this will give us 4 exponential negative j of 5t. So I hope it's clear, yeah? All these issues. Okay then, I'm not going to do these examples. You can try to do it on your own. If you got problem with these examples here, you can refer, you can just inform me, or you can just contact me, yeah, for the solutions. Okay, let's have a look on these final examples for lecture 11. Okay, so we are given these problems. We have the input of the IT. Okay, the input, this is the input to a system of HT, and we are going to get the V naught T, which is the output. And further on, we are given that the Fourier transform for the V naught T is V naught omega, which is sin pi omega minus 4 pi. Okay, and the V1T, the VIT is given to be these signals, which is a sinusoidal signals, but limited only between negative pi and positive pi. So based on this question, we need to obtain what is the VIT in terms of rectangular function. That first question. So let's have a look at the solution for this. So we are given this. Okay, so I can say that the VIT basically can be calculated as a multiplication of two signals, in which the first signal is a sinusoidal signals having an amplitude of 1 over pi and a period of pi over 2. Okay, so you can refer back to the questions here. You can see that based on this diagram, this is 2 periods, yeah? This is 1 period, up to this is 1 period. This is 1 more period, so it's 2 period here. So basically, half of it will be pi over 2. So that's why we have this period of the signals is pi over 2. So the first signal is having is between negative infinite to positive infinite. So in order for us to limit these signals only between negative pi and positive pi, we need to multiply the signals here with a rectangular functions given here, which is having a value between negative pi to positive pi and the amplitude of 1, such that when we multiply these two functions, it will lead back to this VIT as given in the questions, yeah? Okay, so from what we have learned previously, this signal sinusoidal will give us, mathematically, will be 1 over pi cos of 4t. So you can work out for this. If you got questions still, you can contact me. And for this rectangular function, we're going to get rectangular t over 2 pi. I think there should be no problem of finding these rectangular terms, yeah? Okay, so multiplication between these two things will give us VIT as 1 over pi cos of 4t rectangular t over 2 pi. So that answers the first part of the question. Number 2 is to determine the VI omega, which is to obtain the Fourier transform of the VIT. Okay, so I think there should be no problem at all, because it's just based on the Fourier transform properties that we have learned before. So first of all, we need to find what should be the Fourier transform for rectangular t over 2 pi. So based on the table, we are going to get, yeah, the Fourier transform for rectangular t over 2 pi will be 2 pi sin of phi omega. You can refer to the table. Okay, And since for the VIT is multiplication between rectangular function and cosine function, so straight away we can adopt the modulation properties. So modulation states that when we have a multiplication with a cosine function, it will further lead to half x omega minus omega naught plus x omega plus omega naught. So previously, we have x omega as 2 pi sin of pi omega. We have omega naught equals to 4. So this is x omega minus omega naught. And this is x omega plus omega naught. So such that the Fourier transform for the VIT will give us this. Okay? All right, so I hope that's clear on these issues here, yeah? Okay. All right, hopefully it's clear, yeah? Good. So let's have a look on the V naught T, the last one. So V naught T is actually to find the inverse of this V naught omega. Because we are given the V naught omega, so we just need to find what should be the inverse for transform of the V naught T. Okay, so we know that the V naught omega is given to be sin of pi omega minus 4 pi, right? So we know that from the table, yeah, from the table, we don't, let me see. We know that the sin omega, yeah, the sin omega is related to a time domain functions of a rectangular one, yeah, rectangular functions, yeah. So we can see that from the table, a rectangular t over tau will give us a tau sin omega tau over 2. Okay, so what we have to do now is just we take into account the terms here. Yeah, the terms here only. So we have that tau over 2, yeah, tau over 2 will be equals to pi. Okay, so that will give us tau equals to 2 pi. And a tau here equals to 1. Okay, this is 1, so a tau is equals to 1. So we shall have a shall be equals to 1 over tau, which is 1 over 2 pi. So as such, when you substitute both a and tau in these terms here, we're going to get sin pi omega is 1 over 2 pi rectangular t over 2 pi. Okay, and since we have a minus 4 pi there, so we know that this is related to frequency shifting properties. Yeah, you can refer to frequency shifting properties, which states that if we have ft exponential j omega naught t, this will give us f omega minus omega naught. So due to that, we can write that the sin pi omega minus 4 pi, its respective time domain function is 1 over 2 pi rectangular t over 2 pi. We just take this and we just take these terms here, and we need to multiply with exponential terms of exponential j of 4 pi t, such that we're going to have a frequency shifting of 4 pi. So that is our V naught t terms. Okay, yeah. So I'm going to give you a solution of lecture 11 in the e-learning. So by going through the lecture notes, by going through the solutions, and by going through this video, hopefully you can understand well on the topics of properties of Fourier transform in lecture 11. So I will going to end here. So next lecture 12 will be emphasizing on the application of Fourier transform, which will be the last lecture in chapter 3. Okay, we're going to meet again lecture 12 later on. Thank you very much.